I'm sorry. Do you hear me? Do you hear me now? Do you hear me now? Oh, I'm sorry. I forgot to switch on microphone after the previous lecture, so I have to start from the beginning. Thank you for staying with me. So, uh, uh, last time we finished with definition of variance. Variance is somehow a distribution around the mathematical expectation, red line here, uh, and so variance is an expectation of difference between expectation itself and each value that is blue. So difference between blue and red mean, but not differences themselves, but squared differences. This is expectation of difference between each value and expectation x minus ex. So this distance, this distance, this distance, this distance multiplied by corresponding probabilities and squared. In practice, I said that it's easier to calculate variance with expectation of squared x. What is that? Value of this times probability of this value of this squared. So expectation of x squared. So square this value times probability of this point, square this, and so on. So expectation of squared random value x minus squared expectation of this random value. So this is easier to calculate in practice. Actually, we already did it in practice last week on Thursday. So the variance assesses the distance between expectation and points, but not distance itself, but square distance. And the last characteristic of distribution is standard deviation. Standard deviation is squared root from variance. So now we can assess not squared distances, but distances themselves, squared root from squared distances. So concluding, we have what do we have for random value? We have random value as numbers, the probability for each number. This is distribution or distribution law. Then we have distribution function, that is probability of all numbers before given. So distribution function of x 0 is probabilities, sum of probabilities of all x's before this x0. Then for continuous random variables we have distribution density function, or it can be called as probability function or probability density function. So this function for continuous variable, random variable, gives for a point the probability of this point. This is probability density function. And last three characteristics is mathematical expectation or just expectation, EX, variance expectations of squared distances from each number, each value of random variable to the expectation squared, and sigma standard deviation is a squared root from variance, so it accesses not squared but distances themselves. Now uniform rectangular distribution. Let's have a look to some example of continuous and discrete random variables. The first one is a continuous random variable equally distributed in the interval from C to D. So we say not equally but uniformly distributed. This means that probability density function or distribution density function, this is the same, is a constant inside this interval from C to D and 0 outside. In the picture it's like that. This thick line is 0 before C, then some constant, lately we'll see this constant is 0 over D minus C during this interval from C to D, and from D to plus infinity 0 again. I would even start with the previous slide. I would change them. Let me do this. Yes. What is the constant? What is this constant? We can calculate this constant from the normalization condition. As we discussed previously, probability density function is some function, for example this one, that gives us idea what probability is for each number on x-axis, and it actually consists of all numbers with very thin rectangles, so the area under curve is all possible values of random variable. It's infinite number, but if we think in rectangles, this infinity leads us to understanding that if we summarize all cases like integral from minus infinity to plus infinity of this f, so we summarize all possible cases with their probability. This sum overall area under the curve is 1. This is normalization condition for continuous random variable. For discrete random variable it's even easier. Just sum of all probabilities of this of values of discrete random variable equals to 1. Like for tossing dice, we have 6 numbers from 1 to 6, and each number has probability 1 over 6. And if we summarize all cases 1, 2, 3, 4, 5, 6, and summarize probability of those cases, so we will get just 1. So the same meaning is for continuous case. Integral of area under curve integral of probability density function equals to 1. Using this normalization condition, we can calculate what is this constant. Our f is a constant, uniform distribution, and we can move this constant before the integral sign, and then we will have just integral from C to D dx, means integral from C to D 1 times dx. Integral of 1 is x, so constant times x, substitution from C to D is just a constant times this subtraction d minus c, and by normalization condition this equals to 1. So constant can be calculated as 1 over d minus c. This is the level of this line, 1 over d minus c. And if we want to calculate probability of hitting this interval, if we drop a point randomly to the interval from C to D, then we can calculate probability of dropping it inside AB interval. And this probability can be calculated like this: integral from A to B. So we see this is a rectangle, this integral, but nevertheless, integral from A to B of our constant 1 over d minus c, this is probability density function dx, equals to 1 over d minus c times again 1 integral of 1x, substitution from A to B. So this probability of having this point inside this interval AB is just a ratio A difference between A and B, the length of this difference, the rate of length of this difference between A and B, of length of maximal interval C between C and D. Next and very important random value is a normal or Gaussian random variable and corresponding normal or Gaussian distribution. Random variable is normal if its probability density function is like that. In this formula we have two important constants. One of them is A and another one is sigma. When we talk about parametrical statistics, then actually in most cases we understand A and sigma as the parameters. What is A and sigma? A is a mathematical expectation, something like mean between all values of a distribution, mean having the biggest probability. This is top probability. How to calculate this? This top probability is when x equals to A. When x equals to A, then we have 0 here, so E power 0 is 1, so we have 1 over sigma times square root 2 times p, 2 times pi, sorry. What else we can see, we can get from this picture? Look at this probability. If we step to the right and to the left 1 sigma, then area under curve will be 0.68, so more than half, almost 70%. What does it mean? That if we have this random variable, normally distributed random variable, then 70% of values will be inside this interval. If we take all students that participates, not this lecture, but this and previous lecture, we will have about 300 students, and 70%, so 210 students, for example, temperature of those students will be inside this interval. Probably, I guess this is the mean will be 36.6, and I would say this sigma is about 0.1. So about 70% of temperatures of students listening my lectures will be inside 36.5 to 36.7, I would say. If we step twice to the right and to the left, then we will have 95% of students with their temperatures inside this interval. What is this interval? It's about 36.4 to 36.8, and for 3 sigmas between 36.3 to 36.9, if this distribution of temperatures is normal, then we will have 99.7% of them. This is 3 sigma rules actually. So almost everyone, if the distribution is normal, should be between mathematical expectation, mean value, and 3 sigma plus minus distance interval. So these are the examples of probability density function for Gaussian distribution. In the left picture we have the same sigma, the same same distribution, same variance around the mean value, but different expectations. As you see, for the red one it's 0, for A equals to 0, for the violet one 1, and for green one 2, and they look pretty the same shaped. And another case is different sigmas but same expectation. A equals to 1 in all 3 cases, but variances are different, sigmas are different. The more sigma is, like for red one, the lower the top, because as you remember, by normalization condition, area under curve, overall area under curve should be 1, so the taller the curve, the more narrow it is. This is not calculation, it's just a definition. Expectation of x is x times probability density function, and probability density function is this constant can be moved before the integral, and this depending of x part of the density distribution function. It will not calculate this integral, believe me, it's equals to a. And for the variance, I'm sorry, this is Russian notation, let me change it. For variance, this is also just definition of variance. It's expectation of a difference between variable itself and the expectation of its squared times density function, that is this constant times this depending on x part, and this integral equals to squared sigma, and standard deviation is sigma as square root from this value. Widely the standard normal random variable is widely used. This is unmeasured value how to get it from our, for example, temperature, the value of random variable. We subtract a, so move this curve to the 0 and divide by its sigma, so sigma will be equals to 1. This is standardization, subtracting mathematical expectation and dividing standard deviation. So this standard normal random variable has 0 as expectation and 1 as variance, and square root from 1 is 1, 1 as standard deviation. Since 99.7% of x values differs from expectation not greater by 3 sigmas, you remember we did these 3 steps to the right and 3 steps to the left. Then for any x we can write that x z standardized text is between -3 and +3, means -3 sigmas plus 3 sigma, and sigma is 1, with probability 0.997. This is so-called 3 sigma rule. Distribution function for normally distributed random variable is by definition like this, and if we standardize our x, then we will have change in this formula e power minus x minus a squared over 2 sigma squared. If we substitute x by minus I by sigma by z, then we will have squared sorry, it should be z here, so I will change it later. This function, sorry, so this function is tabulated, and this is distribution function for standard normal distribution. We cannot have tabulated tables for all possible values for height, for weight, for temperature, but it can be substituted by z and moved to the tabulated distribution of this standardized normal distribution. This is the z table. In practice we will try to calculate something using this table. For example, if we want to calculate the probability of temperature of the first student that comes to this that have come to this lecture, has temperature less than 36.7, instead of 36.7 we can calculate phi of z, it will be 0.2 as I remember, or just 2, and look and calculate this probability just using this table. In this example, instead of calculation probability of first student, it was Ziyad. So the probability of Ziyad's temperature less than 36.7 we can calculate using this algorithm. So 36.7 minus 36.6 is 0.1 and sigma is 0.1, so z is 1. And this probability can be calculated just looking at the table for z as 1. What is that? So probability of Ziyad's temperature less than 36.7 is 0.84. Are you happy, Ziyad? Should be. So we already saw this probability in this slide when I started discussion about normal distribution. But formally, we can get all these values. I remind 0.68, 0.95 and 99.7 for falling into these intervals plus minus 3 sigma, plus minus 2 sigma, and plus minus 1 sigma, using this table that we just have seen. Let's start from the 1 sigma. So we want to know probability that our random variable is between expectation minus sigma and expectation plus sigma. We move from x to z, like minus expectation over sigma, and now 2 times in this part and that part. This subtraction is from definition of distribution function. Distribution function is a probability of our random value less than some value, and falling inside this interval is just difference between 2 distribution functions for bigger number minus lower number. So ex plus sigma x minus ex over sigma, and the minus distribution function of this value ex minus sigma x, again minus ex over sigma. And it's easy to see that those oddends cancel 2 times, and we see phi of plus 1 minus phi of minus 1, and phi of minus 1 is actually 1 minus phi of 1, and so we have 2 times phi of plus 1 minus 1, and as we just saw that phi on Ziyad's case, we have phi of plus 1 is 0.84, and now we have 0.68. Analogously, we can have those numbers for 2 sigmas and 3 sigmas. The difference between those calculations is just in this middle number. We have 1 sigma, 2 sigma, or 3 sigmas, and then we have phi over 1, phi over 2, and phi over 3. And 3 times looking at the previous table here, here, and here. Sorry. We get 3 probabilities: 0.68, 0.95, and 0.99.7. 99.72. Sorry. So this is for normal distribution and then standard normal distribution. The next distribution is a binomial one. It's discrete, as you see. Its shape looks like normal, but it is not. It's just symmetrical. And what is the binomial distribution? Let's imagine tossing a coin experiment. We can have heads or tails, and if coin is normal, that probability of heads and tails is the same, 0.5. But another binary experiment is, for example, students зачет, and looking back to number of students in this semester, and comparing it for the previous semester, we can say that successfully passing all зачетs and exams in the first semester, the probability of this is about 0.9, I would say. And what is the distribution itself? We want to calculate with what probability we can have 1 or 2 or 5 or 3 and so on successes from, for example, 5 experiments. So we have a number of tossing coins or number of passing, of trying зачет, and then we want to know how many successes and what is probability of concrete number of successes, 3 or so on. And the answer, probability of k successes among n tries, is number of combination binomial coefficients from n of k times probability of success power k, number of successes we want to know, and probability of unsuccess. So q is 1 minus p. The number of unsuccesses is the rest number of experiments after successes. So if we have 5 experiments and want to calculate probability of 3 successes among 5 tries, then and success of the probability of success is 0.9, so it will be 5 number of combinations from 5 3, then probability 0.9 power 3 and 0.1 power 2. This is binomial distribution for different number of experiments and different probability of success. If we have 40 experiments, then it's logically obvious that the most probable result is 20 successes and 20 losers, unsuccesses. And probability of 20 among 40 experiments is the biggest one, but not big, as you see, is just about 12%, I would say. Just why? Because we have 40 experiments and we want to know 20, not less, not more, just 20 successes. If we want, if we have only 20 tries, 20 experiments, look at the blue one, and probability of success is again like with normal coin is 0.5. Then we have bigger probability of 10 than in case of 40 experiments and half of 20 successes. And the last example is 20 experiments and probability 0.7 of success in one experiment. If we have 20 experiments, then most probable value of successes is 14, 7 twice. So, and for 14 we have probabilities about 19%, I would say. The bigger than in both cases for equal probabilities. This is binomial distribution. Another distribution, Poisson distribution. If we are interested in how many successes we have among a lot of experiments for binomial distribution, we talked about 5 experiments and 3 successes. But if we have 500 experiments and 3 successes, then it's almost impossible to calculate probability of 3 successes among 500 by formula with binomial coefficient. For those rare cases, we have another distribution, and number of successes among all number of experiments, 3 among 500, is how to say, compressed, I would say, in lambda, the only parameter of Poisson distribution. Lambda is this more frequent, usual, I would say, value for the this rare event. For example, if we have 500 objects and 3 of them are broken, then lambda will be 3. But if we ask what is the probability of having 6 broken objects from in 1000 of objects, the lambda would move from 3 to 6. So lambda is actually n, a number of experiments, times p, probability of one success or unsuccess in our experiments. If we have 500 objects and 3 of them are broken, it's better to say about unsuccess. And now probability of 3 broken objects among 500 in our task is e power minus 3, then minus sorry again, if we want to calculate, let's see, 4 broken objects, while usually we have 3 broken objects in our set of 500, then lambda is 3, it's a usual number of broken objects, and k is a number of broken objects of our interest. So in order to calculate probability of having 4 broken objects among 500, we should calculate E. This is a base of a natural logarithm. This is just a number. Power minus 3 times 3 power 4, and 4 factorial is a denominator. This is how to calculate probability of 4 broken objects among 500, while it should be usually 3, by Poisson distribution. It's interesting that expectation and variance for Poisson distribution are the same, and they are equal to lambda. And let us come back to examples with Poisson distribution. On the left page we see the probabilities. I cannot say this is probability density function because Poisson distribution is discrete like for binary ones. So this is probabilities for 0, 1, 2, 3 and so on numbers, while lambda is 1, so the maximal probability for 1, for example 1 broken object in 500, the probability of 1 will be about 38%. If usually we find 4 broken objects in 500 of objects, then probability, the maximal probability will be for 4 and close for 3 and so on. If for 10, the maximal probability will be here for 10 and so on. And this is a distribution function, monotonely growing, monotonely increasing. Normal distribution, you remember that it has 2 parameters. Mean, we denoted it is A, here it's mu, and sigma. Again, this is this for green and red ones we have the same expectation, but and for blue one we have the same expectation but different sigmas, and this violet one have another sigma and another expectation. And these are the density function for normal distribution. So sorry, distribution function. This is density functions, this is distribution functions. And student distribution, we will use it a little bit later. We already used it in physics when we assessed the errors of our measurements for not a big number of experiments like 3, 5, 10. We should use students' distribution to assess the error. But when the number of experiments is 30 and more, then student distribution looks like normal, and it's shown with pink color. It's looks like normal actually. analytical representation of probability density function, distribution function is quite complicated with gamma function and other functions, and we will not calculate these, we will use tables. So next slide and next part of our course is mathematical statistics. So we finished with basics of probability theory, and now we go to more practical things to medical students and to scientists is mathematical statistics. In this course we will consider two subjects, hypothesis, statistical hypothesis, and correlations. Statistical hypothesis allows us to find the differences between groups of patients, to prove, to verify, to justify the difference calculated, and to control group and case group before and after some surgical operation, for example, and so on. We cannot say just look, this number is bigger. We should justify it statistically. And correlation is a dependency between two measured parameters. It's a measure of difference, connection between them. So, but first let's introduce some statistical notions. Mathematical statistics itself is a branch of mathematics about methods of registration, systematization, and analysis of statistical experimental data obtained as a result of observation of mass random event. Two very important things is population and sample. Population is a set of similar items for us, patients or events, which is of interest of some question on experiment. Our experiments are medical. This is diagnostic. We want to differ this group of diseased people and this group of healthy people using some parameter, laboratory or physical or something. We cannot observe all people, all diseased patients and all healthy patients, healthy people. Sorry, we can just assess it using some of patients and some of healthy people, and this number selected from all population is a sample. What do we wonder in mathematical statistics? The first thing is determination of distribution of random variable. So what is the distribution? If we know somehow distribution, that how to determine its parameters. For example, if we know that this characteristic distributed normally, that what is the mean, what is the A, and what is the sigma. And third, the problem of verification of the likelihood of proposed statistical hypothesis. Hypotheses is usually the so-called zero hypothesis. Zero hypothesis means that we don't see any difference between diseased and healthy, between those who had some operation, that who didn't have. So zero hypothesis tells us that states, I would say, not tells us, but zero hypothesis states that nothing happened, and we want to reject this hypothesis. We want to say that our intervention leads us to good results, to cure diseased patients. So first step is collecting experimental data to determine a distribution of a random variable necessary to take a series of measurements or calculations for the random variable interesting us. Result is statistical series, and this is the set of numerical data or unnumerical data, and we call it sample of volume n. Then the numbers can be ordered, then we will obtain ordered statistical series and work with this ordered. It can be called ranked, but rank is a term, busy term for another things. So if we measured 10 times something, just like health rate, I guess, we should order to make it easier for future calculations. Fluctuations over studied treat called variation. Our example variation is a change in heart rate. Then we should prepare variation series. We can calculate frequencies of all numbers we met. Here we met 72 times, 83 times, 92 times. This is a discrete variation series. We can represent it graphically. For each number, we can show for each value, we can show the number of this value in our sample. How often we meet this value in our sample. The most often, 80 is met most often. It can be called polygon of frequencies. If those numbers are not integers, they can be any number from the interval, then we can split our axis of all numbers onto some intervals. How many intervals it should be depends on number of experiments. There are several ways to split split the interval where we have all our numbers into subintervals, and the most often used is Sturges formula, binary logarithm of n plus 1, rounded to the top, and squared root, again rounded from n number of experiments. There are other approaches can be studied here in this reference. Then the length of interval can be calculated as maximal minus minimal values of our series over number of intervals. Actually, you will have a laboratory work to study Gaussian distribution, and you will have about 100 numbers, and you will do just this exercise. You will split your numbers, you will calculate, select maximal and minimal, calculate difference between maximum and minimum, and then split this interval of your numbers onto k subintervals, and length of subinterval is like this, delta x. Example. Let's analyze weight of 60 newborns. The minimal is 1.5 kilogram and maximal weight is 5 kilos. Let's take number of intervals is 7, so the delta will be 0.5, and in order to represent our sample, we can construct those intervals starting with minimal 0.5 here, finishing with maximal 5 kilo, and those 7 interval will be just 0.5 kilos each, half of kilo each interval. When you will do this in Excel, you will decide yourself which number, in which interval the boundary number goes. In this example, we have the most frequent newborn weight is from 3 to 3.5, and then almost symmetrically the probability goes down. To the right 14, to the left 12, then to the right 4, to the left 6, and the last number, the smallest weight, and the biggest weight is just 2 babies here and here. Distribution of the population can be assessed or estimated from the sample, and distribution law is the actual probability in populations or in all people having these characteristics, for example, all diseased people from some disease. Here, probability of meeting of these characteristics can be reached when we take samples bigger and bigger. So the bigger sample is, the closer our frequency of meeting of this value of characteristics to the value, to the probability in population. This means that the more patients we involve in our treatment, in our statistical study, the closer result to the true one we will get. Statistical characteristics of population repeats the statistical characteristics for random value, mathematical expectation, value, standard deviation, for the sample, we instead of expectation we have a mean for our sample, because all values met in the sample trees are equal, has equal probability, has equal importance. Then variance as standard deviation squared, but for the sample we have a little bit different from sigma value standard deviation. We'll see a little bit later the formula for this. So this is a difference for population with true expectation, true variance and sigma, and if we have some finite number of patients from this population, expectation corresponds to mean value. This is just mean, sum of values for all patients over n. Standard deviation for population is like this, xi minus expectation over n. This is so if we apply this to sample, we will have something called biased variance, and in order to have unbiased, we should divide by n minus 1, and this is standard deviation itself, squared root from variance. Mean error is calculated like this. Mean error is, or standard mean error is standard deviation over square root of n. You can remember this formula is a part of calculation on physics, calculation of error of our measurements. So arithmetic or mean error shows, standard mean error shows how close the sample arithmetic mean of measured characteristics to expected value. The larger the sample size, the closer the arithmetic mean to expectation of the overall population. So this statement is a variant of a law of large numbers. It's usually denoted like LLM. Along with expectation, we want to know, for example, in physics experiment, what is deviation for allowed for our random variable. So we want to know how big is the difference between mean value and our expectation when we measured something on just a sample. So along with points estimates, interval estimates of parameters of the population are used. Interval population, so x minus delta x and x mean value of x plus delta x forms the interval for expectation. We can reformulate this formula moving ex and x mean, and we will have this expression. So our mean is inside the expectation. We don't know it, we have just sample, but this is expectation for population minus delta x and expectation plus delta x. So we want to know the boundaries of this interval, calculating delta x. This is the same thing for we want to know the probability of getting our mean value for our sample inside this interval assessed from expectation of populations. In practice, we need to solve inverse problem to determine the boundaries of interval. We don't know them. To determine the boundaries of interval, it's necessary to predefine probability with which we will determine this interval. So we state probability this, and then we will calculate deltas depending on this probability. So this probability is called confidence probability, and interval is called confidence interval. Actually, confidence interval is the interval that we measured, that we calculated on physics for error in our experiments. Confidence interval of any parameter is an interval which contains this parameter with the probability of p confidence. This is confidence probability. Usually confidence probability is taken as 0.95 for small samples. For bigger samples starting from I would say 50, we should use another confidence probability 0.99. For 1,000, for hundreds, even 0.39. Along with probability, confidence probability, the level of significance goes. Level of significance or first type error is the addition to the 1 for confidence probability. So confidence probability plus level of significance is 1. Level of significance is the probability the value of studied parameter is not inside the confidence interval. A lot of random variables in biology and medicine are normally distributed. So using knowing probability, confidence probability in our study, we can calculate delta as using formula for standard normal deviation distribution. In this case, if we want to know probability as 0.95, then we should divide 0.95 plus 1 over by 2 and have this probability. For small samples, and the distribution can differ from normal one, can differ significantly. And thus William Gosset proposed student distribution. We mentioned it several times. Student normalized random variable is calculated by the formula, and the probability density of this random variable is like this student distribution. You remember this is a complicated parameter with gamma function. We will not consider it. We will use tables to calculate values for student distribution. Practical interval instead of normal one, we use the student one. As you remember, we on physics we multiplied our mean error value, calculated as like this. We multiplied by student table value. This is actually a value of student distributed random variable. As a result of our experiments, we concluded that our estimated value from our experiments lies between these boundaries of the interval. In the middle of the interval, our experimented value, mean value, and plus and minus error based on student distribution. These are student coefficients, and you can see that if the number of experiments goes more and more, bigger and bigger, then it tends to normal distribution actually. Consider an example. Determinant of protein concentration in the solution. The following results are obtained in milligram by liter. You see those numbers, and the problem is to find mean, standard deviation, and confidence interval for student confidence interval for probability of 0.95. Why student? Because the number of experiments of numbers is much smaller than 30. So the mean value is, you see, 112.8. Then we should subtract this mean value from each number, from this, and that, and summarize squared subtraction, and divide on 4. So we'll have 1.92. After that, we should divide standard deviation on square root of n, and we will have standard mean error. So it will be 86, sorry, and after that we can assess the error like student coefficient 2.8 times our standard error. And finally, the delta statistical delta is 2.4, and the answer is 112.8 plus and minus 2.4 milligram per liter. Why 2.8? Because we had 5 experiments, and looking here number of measurements 5, and now and probability and confidence probability 0.95. So actually this is wrong. Should be not significance level but confidence probability, and here we have 2.8, just like in our formula. So, and this is the result. Ex can be assessed like this after our experiment. Well, algorithm for processing result of direct measurements is the following. I remind because we did it last semester, but now more from statistical point of view. First do measurements, find the arithmetic mean, then calculate random error like we just did, t-student times standard mean error, then find the systematic error. If the device has precision class, then we use it. Precision class times maximum on the device's scale over 100%, and if device does not have precision class, like a ruler, sorry, then this systematic error is half of division of the ruler is its usual ruler, that division value is 1 millimeter, so systematic error will be half of millimeter. And then we calculate absolute error as a sum of two random and systematic squared. We'll talk later then that those random variables are independent, so we can calculate like this, just a square root from squared values, and final result, the actually in our terms the estimation of population. So this estimation of real value of the parameter measured in experiments is x mean plus and minus delta x absolute error for confident probability 0.95. And as we talked in previous semester again, then we should access relational error or relative error. It's not the coefficient of variation, and this relative error represented as a percentage should be less than 20. Well, let's make a break and don't want to start new subject. Anyways, it's time to finish. So see you in 40 minutes in the next lecture.